Alrighty, we're almost finished with chapter 5, just a couple more sections. This one is a special section which I've inserted because I think it's a lot easier to break the complex topic that's coming up soon into two pieces. So in this section, which I've labeled 8-point star, it's not in your book anywhere, but I've kind of just created it to help you out. It's how to graph the basic rational function, because the type of graph that it is and how it looks is very different than anything you've seen before. Up until this point, we've been graphing a lot of straight lines and a lot of parabolas, and this graph has very different properties. So first, we're going to do a little miniature lesson on how to graph y equals 1 over x, which is the simplest possible rational function you can get. And then in the next section, we'll dive into really what rational functions are and the different complications that can arise. But before we do that, I want you to have a visual idea of what the graph looks like and why it looks the way that it does. So remember, we've actually seen this before. You've seen the equation y equals k over x before, and that was called inverse variation. Hopefully you remember that. And the thing with inverse variation was that when one of the variables went up by a certain ratio, the other variable went down by the same ratio. And so the same is going to happen when you graph it. If the x value increases, the y value is going to decrease. And that's going to lead to a very unique shape. So to kind of discover what that shape is, we're going to make a t-table. And using this equation, it should be very simple and quick and easy. We're going to plug in x values into this equation and see what we get out for y. So if you plug in x as 1, right here, 1 divided by 1 is 1. So the point 1 comma 1 has to be on the graph. If you plug in x as 2, 1 divided by 2 is 1/2. And again, this matches up our idea of inverse variation. The x value doubled, the y value got cut in half. If x is 3, y is 1/3. What if x is 1/2? 1 divided by 1/2. Let's do that real quick. 1 divided by 1/2. Remember that when you divide by a fraction, that's the same as multiplying by the reciprocal. So that's the same as 1 times 2 over 1, and 1 times 2 is 2. So when the x value got cut in half, the y value was doubled. Alright, and last one we'll do is 1/3 comma 3. Okay, so you get this kind of idea that if the x value is getting bigger, the y value is getting smaller. But if the y value is, or sorry, if the x value is getting smaller, the y value is getting bigger. I also want to do a t-table, same exact numbers, but negative. I mean, there's no reason you can't plug in a negative number here. So if x is -1, 1 divided by -1 is -1. If x is -2, 1 divided by -2 is -1/2. -3, -1/3. And you can finish this off, -1/2, -2, -1/3, -3. So there's an exact parallel on the negative side and the positive side. If the input is positive, the output is positive. If the input is negative, the output is negative. And you want to write down the definition of an asymptote here, and then when I draw the picture for this graph, I'll explain what it looks like. But this graph is going to have an asymptote, and an asymptote is a straight line that the graph approaches but does not cross. So let's draw the graph, and then I'll show what the asymptotes are. Okay, so here's our graph. The points that we had were 1, 1. Let's label this as 1, 2, 3, 1, 2, 3. 1, 1, over 2 up a half, over 3 up a third, over a half up 2, and over a third up 3. So you can see these are kind of forming a nice curve, so I'll try to draw it in as best I can. And this line here, it's getting closer and closer to 0, but it's never going to cross, because imagine if you went over to an x value of, here's x equals 7, right? How high do I go? 1 divided by 7 is up 1/7. If I went all the way over to an x value of 100, I'd still go up 1/100th. If I went over to a billion, I still go up 1/1,000,000,000th. So it's getting really, 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 really flat and really close to 0, but it's never actually quite getting to 0. So this line is getting really close. And then on this side, if I make the x value input 1/100th, I go up 100. So the closer I get to the y-axis, the higher my graph is going, but it's never actually going to cross, at least right here. So this is going to go up and up and up and up. So what actually happens, here let me change my color, is this axis itself and this axis itself these are acting as asymptotes. So that's the thing that you just defined on the previous slide. Asymptotes, they're the lines that your graph is getting closer and closer to but never crossing. And in this case, by pure coincidence, the two asymptotes happen to be the x and y axis. But that doesn't have to be the case. It could, the asymptotes that you use to draw the lines, they don't have to be the axes. If you, for example, slid this entire graph sideways and up, then the asymptotes would no longer be on the axes. So we also need to draw in the negative side. So we had -1, -1, -2, -1/2, -3, -1/3, -7, -1/7. So it's getting really close. -1/2, -2, -1/3, -3, -1/7, -7, like this. So it's really close. Then it curls this way. And then again, it's really close, but not quite crossing. So really close, but not quite crossing. And so collectively, this part and this part make up the graph. If you only graph 1/2 of it, you've not completed the whole thing. You need to graph both sides. That's really important. And you just have to remember this idea. You know, you can draw a t-table if you want to help remind yourself, but you really should, in your head, you should know that when one thing is getting bigger, the other is getting smaller. So you've got 1, 1, 2, 1/2, 3, 1/3, and the pattern just continues because it's inverse variation. Okay, and the asymptotes are the lines that you approach but do not cross. A lot of times, when you're doing a graph like this, you actually draw in the asymptotes first and use those to help guide your curve that you're drawing. And we'll get to that a lot in the next section. But this is it. This is the basic graph. This is called inverse variation, which is an example of a rational function. So inverse variation is the simplest possible example of a rational function. And we're going to be getting more complicated ones in the following section.